So I was really excited to discover that we can use OpenCV, which is something I've wanted ever since we had to throw it away from FastAI. And so I thought, you know, what would it take to create a data blocks API with OpenCV? And thanks to Alexis Gallagher, who kind of gave us the great starting point to say, well, here is what a Swifty style data blocks would look like. We were able to flesh it out into this complete thing. And when Chris described Alexis to me as the world leader on value types, and I was like, wait, I thought you created them. I thought, okay, I guess we can listen to Alexis's code for this. So
I will say I'm terrified about presenting those slides because Alexis is sitting right there, and if he starts scowling, then
we have a handheld mic. Come and correct us anytime. So there's a thing here called OC data block generic, where you'll find that what we've actually done is we've got the entire data blocks API in this really interesting Swifty style. And what you'll see is that when we compare it to the Python version, this is, on every axis, very significantly better. So let's talk about some of the problems with the data block API in Python. I love the data block API, but lots of you have rightly complained that we have to run all the dot blah, dot blah, dot blah in a particular order. If we get the wrong order, we get inscrutable errors. We have to make sure that we have certain steps in there. If we miss a step, we get inscrutable errors. It's difficult to deal with at that level. And then the code inside the data blocks API, I hate changing it now because I find it too confusing to remember like why it all fits together. But check out this Swift code that does the same thing, right? So is that don't load. This is just the same get files we've seen before. All we need to do is we say, you know what, if you're going to create some new data bunch, you need some way to get the data. You need some way, and let's assume that they're just paths for now. You need some way to turn all of those paths into items, so something like our item list in Python. You need some way to split it between training and validation. And you need some way to label the items. Right? So for example, for ImageNet, download calls that. And things that convert paths to images, which grab all of the list of paths is that collect files. And then the thing that converts, that decides whether they're training or validation is whether the parent.parent is train or not. And the thing that creates the label is the parent. And so like we can basically just define this one neat little package of information and we're done. And Swift will actually tell us if we forgot something, or if one of the things that we provided, like is training is meant to return true or false if it's training or validation. If we return, like accidentally return the words train instead, it'll complain and let us know. So like, I just love this so much. But to understand what's going on here, we need to learn a bit more about how Swift works and this idea of protocols.
Yeah, so this is something that is actually useful if you are doing deep learning stuff. So let's talk about, go for it. So let's talk about what protocols are in Swift. So we've seen structs. We will see classes later, but right now we want to talk about what protocols are. And if you've worked in other languages, you may be familiar with things like interfaces in Java. Abstract classes are often used. Advanced other weird languages have things called type classes. And so all these things are related to protocols in Swift. And what protocols do is they're all about splitting the interface of a type from the implementation. And so we'll talk about layer later. Layer is a protocol, and it says that to use a layer, or to define a layer, you have this call. So layers are callable, just like in PyTorch. And so then you can define a dense layer and say how to call a dense layer. You can define a conv2d and show how to implement a conv2d layer. And so there's a contract here between what a type is supposed to have. All layers must be callable, and then the implementations of these are different. Right, so this is pretty straightforward stuff.
Although even that's quite nice, right? Because like in PyTorch, you kind of have to know that there's something called forward, and if you misspell it or forget it to put it there or put done to call instead of forward, you get kind of weird inscrutable errors, whereas with this approach,
you get tab completion for the signature.
Yeah, instead Swift will tell you if you get it wrong. It'll say, this is what the function should have been called.
Yeah, that's great. And so what this is really doing is this is defining behaviors for groups of types. And so we're saying a layer is like the commonality between a whole group of types that behave like a layer. And what does that behavior mean? Well, it's a list of what are called requirements. And so these are all the methods that the type has to have. This is the signatures of the types. And these things often have invariants. And so one of the things that Swift has in its library is the notion of equatable. What is equatable? Well, an equatable is any type that has this equals equals operator, right? And then it says what is equatability and all that kind of stuff. Now, the cool thing about this is that you can build up towers of types. And so you can say, well, equatable gets refined by an additive arithmetic. And an additive arithmetic is something that supports addition and subtraction. Then if you also have multiplication, you can be numeric. And if you also have negation, then you can be signed. And then you can have integers, and you can have floating point. And now you can have all these different things that exist in the ecosystem of your program, and you can describe them. And so this is all very... these things, these ways to reason about these groups of types, give you the ability to get these abstractions that we all want.
And these types already exist in Swift.
And these all exist, and you can go see them in the standard library. And so why do you want this? Well, the cool thing about this is that now you can define behavior that applies to all of the members of that class. And so what we're doing here is we're saying not equal. Well, all things that are equatable, and this T colon equatable says, I work with any type that is equatable. What this is doing is this is defining a function, not equal, on any type that's equatable, and it takes two of these things and returns a bool. And we can implement not equal by just calling equals equals, which all equatable things are, and then inverting it.
So to be clear, what Chris just did here was he wrote one function that is now going to add behavior to every single thing that defines equals automatically, which is pretty magic.
Just like everywhere, boom, one place, super abstract. But this also works for lots of other things. This works for like absolute value. What does absolute value need? Well, it needs any type that is signed and numeric and that's comparable. And how do you implement absolute value? Well, you compare the thing against 0. If it's less than 0, you negate it. Otherwise, you return it. Like super simple. But now everything that is a number that can be compared is now absable. Right? Types, same thing. All these things work the same way. And so with dictionary, what you want is you want the keys in a dictionary all have to be hashable. This is how the dictionary does its efficient lookups and things like that. The value can be anything, though. And so all these things kind of stack together and fit together like building blocks. One of the really cool things about this now is that we can start taking this further. So we talked about not equal building on top of equal. In the last lesson, we defined this is-odd function. We defined it on int. Well, because this protocol exists, we can actually add it as a method to all things that are binary integers. And so we can say, hey, put this on all binary integers and give them all an is-odd method. And now I don't have to put is-odd on int and int16 and int32 and the C weird things. And we could just do it in one place, and now everybody gets this method, right? On layers, right? This is something that's closer to home. Here we can say, hey, I want a inferring from method that does some learning phase switching magic nonsense. But now because I put this on all layers, well, I can use it on my model because your model's a layer, my dense layer, that's a layer. And so this thing allows this one simple idea of defining groups of types and then broadcasting behavior and functionality onto all of them at once is really powerful.
Yeah, I mean, it's like Python's monkey patching, which we use all the time, but A, it's not this kind of hacky thing with weird undefined behavior sometime, and B, we don't have to monkey patch lots and lots of different places to add functionality to lots of things. We just put it in one place, and the functionality gets sucked in by everything that can use it.
Yeah, and remember, extensions are really cool because they work even if you didn't define the type. And so what you can literally do is you can pull in some C library, not that we love C, but with some C library, and add things to its structs. I mean, this is,
Or have things automatically added to those structs because
Absolutely.
it already supports those operations.
yeah, so like all this stuff composes together in a really nice way, which allows you to do very powerful and very simple and beautiful things. So mixins show up and you can control where they go. And so here's an example. This is something that Jeremy wrote. And so he defined his own protocol, countable. And he says, things are countable if they have a variable named count. And the only thing I care about for countable things is I can read it. I don't have to write it. That's what the get means. And so he says, arrays countable. His OpenCV mat thingy is countable. Like all these
number of pixels in it, yep.
Yeah, all these things are countable. And then Jeremy says, hey, well, take any sequence. Let's add a method or a property called total count to anything that's a sequence.
So a sequence is the same as Python's iterable, so anything you can iterate through.
Exactly. And so this is things like dictionaries and arrays and ranges and like all these things are sequences. And it says that so long as the element is countable, so I have an array of countable things, then I can get a total count method or a property, right? And the way this is implemented is it just says, hey, map over myself, get the count, add all the counts up together, and then I have a total count of all the things in my array. And now if I have an array of arrays, an array of mats, a lazy mapped collection sequencey thingy of mats, whatever it is, now I can just ask for its count or its total count.
Hey, Chris, this, so this functionality you're describing is basically the same as what Haskell calls type classes?
Yes.
Is that right?
Yeah.
So is this kind of like stolen from Haskell?
It's borrowed.
I mean, so the interesting thing for me here is
We let them play with it too.
well, the interesting thing, the reason I ask is because like I've tried to use Haskell before many times and have always failed. I'm clearly not somebody who's smart enough to use Haskell. Yet I wrote the code that's on the screen right now like a couple of days ago, and I didn't spend a moment even thinking about the fact I was writing the code. It was only like the next day that I looked back at this code and I thought like, wow, I just did something which no other language I've used both could do and I was smart enough to do it. Like it kind of makes this, what I think of as like super genius functionality available to normal people.
Yeah, and so back at the very, very beginning of this, we talked about Swift's goal is to be able to take good ideas wherever they are and assemble them in a tasteful way and then be not weird. Like being not weird is a pretty hard but important goal. So the way I look at programming languages is that programming languages in the world have these gems in them. And Haskell has a lot of gems, incidentally. It's a really cool functional language. It's very academic. It's super powerful in lots of ways. But then it gets buried in weird syntax. And it's this purely functional, you have to be, has a very opinionated worldview of how you're supposed to write code. And so it appeals to a group of people, which is great. But then it gets ignored by the masses. And to me, it's really sad that the great technology in programming languages that's been invented for decades and decades and decades gets forgotten just because it happened to be put in the wrong place.
Yeah,
so
I mean, it's not just that, but it's even the whole way things are described are all about monoids and monads and whatever.
Existentials and things like that. Yeah, exactly. And so a lot of what Swift is trying to do is trying to take those ideas, re-explain them in a way that actually makes sense, stack them up in a very nice, consistent way, and design it, right? And so a lot of this was pull these things together and really polish and really push and like make sure that the core is really solid.
Okay, we have a question. How does the Swift protocol approach avoid the inheritance tree hell problem in languages like C#, where you end up with enormous trees that are impossible to refactor?
Yes.
And similarly, what are the top opinions around using the Mixin pattern, which has been found to be an anti-pattern in other contexts?
Yeah, so the way that Swift implements this is completely different than the way that subclasses work in C# or Java or other object-oriented languages. There, what you get is something called a vtable. And so your type has to have one set of mappings for all these different methods, and then you get very deep inheritance hierarchies. In Swift, you end up adding methods to int. Like, so we, on the last slide, added a method is_odd to all the integers. Integers don't have a vtable. That would be a very inefficient thing to do. And so the implementation is completely different. The trade-offs are completely different. I will, at the end of this, I think, in a couple of slides, have a good pointer that will give you a very nice deep dive on all that kind of stuff. So also there's the binary method problem, and there's a whole bunch of other things that are very cleanly solved in Swift protocols.
Okay, and then there was also a question, out of curiosity, could you give an estimate of how long it would take someone to go from a fair level of knowledge in Python, TensorFlow deep learning, to start being able to be a competent contributor to Swift for TensorFlow?
Yeah, so we've designed Swift in general to be really easy to learn, and so that you can learn as you go. And this course is a little bit it's very bottoms up, but a lot of Swift, just like Python, was designed to be taught. And what you start with when you go in from that perspective is you get a very top-down kind of perspective. And what I would do is I would start with the Google for a Swift tour, and you get a very nice top-down view of the language, and it's very approachable.
And like, just pick something that like is in FastAI, in some FastAI notebook now. We haven't implemented it yet. And pop it into a notebook, right? And the first time you try to do that, you'll get all kinds of weird errors and abstractions, and you won't know what's going on. But after a few
Ask
weeks,
on the forum, and that's what the community is about.
Yeah, lots of help from the forum, and Chris and I are both on the forum, and there's SOTF teams on the forum. We'll help you out, and in a few weeks' time, you'll be writing stuff from scratch and finding it a much smoother process.
Yeah. So I want to address one weird thing here and give you something to think about. And you might wonder, okay, well, Jeremy wants to know all the countable things. We have arrays and we have mat, and we have to say that they are countable. But the compiler knows that it's countable or not. Like if you try to make something countable and it doesn't have a count method, the compiler will complain to you. So why do we have to do this? Well, let's talk about a different example. And the answer is that protocols are not just about methods. And this is also related to the C# question. But the behavior of those methods also matters. And so here we're going to switch domains and talk about shapes. And so I have shape. All shapes have to have a draw method. Right? This is super easy. And what I can do is I can define an octagon and tell it how to draw. I can define a diamond, tell it how to draw, using exactly the same stuff that we just saw before. Really easy. And the cool thing about this is now I can define a method, refresh, and now refresh, all it does is it clears the canvas and draws the shape. And so all shapes will get a refresh method. And so if you go do a tab completion on your octagon, it all just works. But what happens if you have something else with the draw method? So cowboys know how to draw. It's a very different notion of what drawing is, right? We don't want cowboys to have a refresh method. It doesn't make sense to clear the screen and then pull out a gun. That's not what we're talking about here. And so the idea of protocols is really, again, to categorize and describe groups of types. And one of the things that you'll see, which is kind of cool, is you can define a protocol with nothing in it. So it's a protocol that doesn't require anything. And then you go say, I want that type, that type, that type, that type to be in this group. And I will have a way to describe that group of types that can be totally random, whatever makes sense for you. And then you can do reflection on it. You can do lots of different things that now apply to exactly that group of types.
And I actually found, I still find, that this kind of protocol-based programming approach is like the exact upside-down opposite of how I've always thought about things. It's kind of like you don't create something that contains these things, but you kind of like, I don't know, somehow shove things in. And the more I've looked at code that works this way, the more I realize it tends to be clearer and more concise, but I still find it a struggle because I just don't have that sense of this is how to go about creating these kinds of APIs. And
one of the things you'll notice is that we added this protocol to array in an extension, right? So unlike interfaces in a Java or C# type of language, we can take somebody else's type and then make it work with the protocol after the fact. And so I think that's a superpower here that allows you to work with these values in different ways. So this is a super brief, high-level view of protocols. Protocols are really cool in Swift, and they draw on a lot of great work in the Haskell and other communities. There's a bunch of talks, and even Jeremy wrote a blog post that's really cool that talks about some of the fun things you can do.
Won't extensions make code hard to read? Because once a functionality of a particular API or class is extended in this way, you won't know if the functionality is coming from the original class or from somewhere else.
Yeah, so that's something you let go of when you write Swift code. And there's a couple of reasons for that. One of which is that you get good IDE support. And so, again, we're kind of building some parts of this airplane as we fly it, but in Xcode, for example, you can click on a method and jump to the definition. Right, and so you can say, well, okay, here's map on array. Where does map come from? Well, map isn't defined on array. Map, filter, reduce, those aren't defined on array. Those are actually defined on sequence. And so all sequences have map, filter, reduce, and a whole bunch of other stuff. And so arrays are, of course, sequences, and so they get all that behavior. And so the fact that it's coming out of sequence, as a Swift programmer, particularly when you're starting, doesn't really matter. It's
And actually, you know,
good functionality.
we've had this same discussion around Python, which is like, oh, Jeremy imports star, and therefore I don't know where things come from, because the only way I used to know where things come from is because I looked at the top of a file and it would say from blah import foo, and so I know foo comes from blah. And we had that whole discussion earlier lesson where I said, that's not how you figure out where things come from. You learn to use jump to symbol in your IDE, or you learn to use Jupyter Notebook's ability to show you where things come from. That's just the way to go.
Thank you. I feel that Scala is often a very nicely designed language that, to my knowledge, doesn't lack in terms of the features I've seen so far in Swift. Is that true? And if so, is the choice of Swift more about JVM as opposed to non-JVM runtimes and compilers?
Yeah, so Scala is a great language. Scala is one of the way I explain Scala is that they are very generous in the features they accept. They're undergoing a big redesign of the language to kind of cut it down and try to make the features more sensible and stack up nicely together. Swift and Scala have a lot of similarities in some places, and they diverge wildly in other places.
I mean, I would say there's a, you know, I feel like anybody doing this course understands the value of tasteful curation, because PyTorch is very tastefully curated, and TensorFlow might not be. And so, like, using a tastefully curated, carefully put together API like Swift has and like PyTorch has, I think it makes life easier for us as data scientists and programmers.
Yeah, but I think the other point is also very good. So Scala is very strong in the JVM, Java virtual machine ecosystem, and it works very well with all the Java APIs, and it's great in that space. Swift is really great if you don't want to wait for JVM to start up, so you can run a script. Right, and so there's nice duals, and they have different strengths and weaknesses in that sense.
Do we have time before our break that I can quickly show how this all goes together? Great.
I probably can't stop you even if I wanted to.
So just to come back to this 8C, right? You can basically see what's happened here. We've defined this protocol saying these are the things that we want to have in a data blocks API. And then we said here is a specific example of a data blocks API. Now at this point, we're missing one important thing, which we've never actually created the bit that says this is how you open an image and resize it and stuff like that, right? So we just go through and we can say, let's call .download, let's call .getItems. We can create nice simple little functions now. We don't have to create complex class hierarchies to say things like, tell me about some sample, and it prints it out, right? And we can create a single little function which creates a train and a valid. This is neat, right? This is something I really like about this style of programming is this is a named tuple. And I really like this idea that we don't have to create our own struct and class all the time. It's a kind of a very functional style of programming where you just say, I'm just going to define my type as soon as I need it. And this type is defined as being a thing with a train and a thing with a valid. So as soon as I whack brackets around, parentheses around this, it's both a type and a thing now. And so now I can partition into train and valid, and that's returned something where I can grab a random element from valid and a random element from train. We can create a processor, and again, it's just a protocol, right? So remember, a processor is a thing like for categories, creating a vocab of all of the possible categories. And so a processor is something where there's some way to say, like, what is the vocab? And if you have a vocab, then process things from text into numbers, or deprocess things from numbers into text. And so we can now go ahead and create a category processor, right? So here's like, grab all the unique values, and here's label to int, and here's int to label.
Why are you using parentheses on your map, Jeremy? Gosh.
I didn't write that. There we go. Yeah. So now that we have a category processor, we can try using it to make sure that it looks sensible. And we can now label and process our data. So we first have to call label, and then we have to call process. Now, given that we have to do those things in a row, rather than creating whole new API functions, we can actually just use function composition. Now, in PyTorch, we've often used thing called compose. But actually, it turns out to be much easier, as you'll see, if you don't create a function called compose, but you actually create an operator. And so here's an operator, which we will call compose, right, which is just defined as first call this function, f, and then call this function, g, on whatever the first thing you passed it is. So now we've defined a new function composition which first labels and then processes. And so now, here's something which does both, and so we can map, right? So we don't have to create, again, all these classes and special purpose functions. We're just putting together function composition and map to label all of our training data and all of our validation data. And so then finally, we can say, well, this is the final structure we want. We want a training set, we want a validation set, and let's again create our own little type in line. Right, so
an array of tuples.
Yeah, so our training set's an array of named tuples, our validation set is an array of named tuples, and so we're going to initialize it by passing both in. And so this basically is now our data blocks API. There's a function called make split labeled data, and we're just going to pass in one of those configuration protocols we saw. So we're going to be passing in the ImageNet configuration protocol, the thing that conforms to that protocol. And we're going to be passing in some processor, right, which is going to be a category processor. And it's just going to call download, get the items, partition, map, label of, and then initialize the processor state, and then do label of, and then process is our processing function, and then map that, right? And so that's it. So now we can say, to use this with OpenCV, we define how to open an image. There it is. We define how to convert BGR to RGB, because OpenCV uses BGR. That's how old it is. We define the thing that resizes to 224 by 224 with bilinear interpolation. And so the process of opening an image is to open, then BGR to RGB, and then resize, and we compose them all together. And that's it, right? So now that we've got that, we then need to convert it to a tensor. So the entire process is to go through all those transforms and then convert to a tensor. And then I'll skip over the bit that does the mini batches. There's a thing we've got to do the mini batches with that split labeled data we created, and we then just pass in the transforms that we want, and we're done, right? So the data blocks API in kind of functional-ish, protocol-ish Swift, ends up being a lot less code to write and a lot easier for the end user, because now for the end user, there's a lot less they have to learn to use this data blocks API. It's really just like the normal kind of maps and function composition that hopefully they're familiar with as Swift programmers. So I'm really excited to see how this came out, because it solves the problems that I've been battling with for the last year with the Python data blocks API, and it's been, really just a couple of days of work to get to this point.
And one of the things that this points to in Swift that is a big focus is on building APIs. And so, again, we've been talking about this idea of being able to take an API, use it without knowing how it works. It could be in C or Python or whatever, but it's about building these things that compose together and they fit together in very nice ways. And with Swift, you get these clean abstractions. So once you pass in the right things, it works. You don't get the stack trace coming out of the middle of somebody else's library that now you have to figure out what you did somewhere along the way that caused it to break.
Yeah.
At least not nearly as often.
So to see what this ends up looking like, I've created a package called datablock. It contains two files in. It's got a package.swift and it's got a main.swift. And main.swift is that, right? So all that in the end to actually use it, that's how much code it is to use your data blocks API and grab all the batches. So it comes out super pretty.
Yeah.
So let's take a 5-minute break and see you back here at 8:05. Okay, so we're gradually working our way back to what we briefly saw last week, Notebook 11, training ImageNet, and we're gradually making our way back up to hit that point again. it's a bit of a slow process because along the way we've had to kind of invent float and learn about a new language and stuff like that. But we are actually finally up to 0.2, a fully connected model, believe it or not. And the nice thing is, at this point, things are going to start looking more and more familiar. One thing I will say, though, that can look quite unfamiliar is the amount of typing that you have to type with Swift. But there's actually a trick, which is you don't have to type all these types.
You don't have to
Swift.
type types.
What you can actually do is you can say, like, oh, you know, here's a type I use all the time, tensor bracket float, and I don't like writing angle brackets either. So let's just create a type alias called TF. And now I just use TF everywhere. Now, to be clear, a lot of real Swift programmers in their production code might not like doing that a lot. I mean, personally, I do that a lot, even not in notebooks. But, you know, you might want to be careful if you're doing actual Swift programming.
The way I would look at it is if you're building something for somebody else to use, if you're publishing an API, you probably don't want to do that.
Yeah.
But if you're hacking things together and you're playing and having fun, it's no problem at all.
Yeah, I mean, different strokes. I personally, I would say if I'm giving somebody something that's the whole thing's tensor floats, I would do it. But anyway, in a notebook, I definitely don't want to be typing that. So in a notebook, make it easier for your interactive programming by knowing about things like type alias.
Yeah, that's something we also want to make better just in general, so that these things all just default to float.
Yeah.
You don't have to worry about it.
That'll be nice. So then we can write a normalized function that looks exactly the same as our Python normalized function. And we can use mean and standard deviation just like in Python. And we can define tests with asserts just like in Python. So this all looks identical. We can calculate n and m and c, the same constant, the variables that we used in Python in exactly the same way as Python. We can create our weights and biases just like in Python, except there's a nice kind of rule of thumb in the Swift world, which is anytime you have a function that's going to create some new thing for you, we always use the init constructor for that. So for example, generating random numbers and dumping them into a tensor, that's constructing a new tensor for you. So it's actually, you're actually calling TensorFloat.init here. And so if you're trying to find where is it in an API that I get to create something in this way, you should generally look for in the init section. So this is how you create random numbers in Swift for TensorFlow. It's how you create a tensor of zeros in Swift for TensorFlow. So here's our weights and biases. This is all the same stuff. We just basically copied and pasted it from the PyTorch version with some very, very minor changes. Create our linear function, except rather than @ we use dot, because that's what they use in Swift for TensorFlow. If you're on a Mac, that's option 8. If you're on anything else, it's compose key dot equals. And so now we can go ahead and calculate linear functions. We can calculate ReLU exactly the same as PyTorch. We can do proper chiming init exactly like PyTorch. And so now we're at the point where we can define the forward pass of a model. And this looks basically, again, identical to PyTorch. A model can just be something that returns some value. So the forward pass of our model really just builds on stuff that we already know about, and it looks almost identical to PyTorch, as does a loss function, right? It looks a little bit different because it's not called squeeze, it's called squeezing shape, but other than that, mean squared error is the same as PyTorch as well. And so now here's our entire forward pass. So hopefully that all looks very familiar. If it doesn't, go back to 0.2 in the Python notebooks. And actually this is one of the tricks, like this is why we've done it this way for you all, is that we have like literally kind of these parallel texts. You know, there's the Python version, there's the Swift version, so you can see how they translate and see exactly how you can go from one language and one framework to another. That's all very well, but we also need to do a backward pass. So to do a backward pass, we can do it exactly the same way as, again, we did it in PyTorch. One trick we kind of Python hack we used in PyTorch.
And so this is doing it the hard way. This is doing it all manually because we have to build it.
Doing it all manually, yep, because we have to build everything from scratch. And the PyTorch version, we actually added a .grad attribute to all of our tensors. You're not allowed to just throw attributes in arbitrary places in Swift, so we have to define a class which has the actual value and the gradient. But once we've done that, the rest of this looks exactly the same as the PyTorch version did. Here's our MSc grad, our ReLU grad, that's all exactly the same. And in fact, you can compare here, right? Here's the Python version we created for lingrad. Here's the Swift version for lingrad. It's almost identical, okay? So now that we've done all that, we can go ahead and do our entire forward and backward pass, and we're good to go. But it could be so much better.
Well, you skipped past the big flashing red lights that says, don't do this. Did you miss that part?
Tell me about it.
Oh, okay. So let's talk about this. So this is defining a class and putting things in classes, and we haven't seen classes yet, at least not very much.